The test for difference in proportions compares two population proportions. Each observation has a binary response, and the explanatory variable tells us which group the observation belongs to. This method is common in clinical trials, marketing experiments, and ecological studies. The main question is whether the difference seen in the sample is large enough to suggest a real difference in the populations. This diagram shows the overall setup. We are comparing two groups on a binary outcome. Let P sub 1 and P sub 2 represent the population proportions for the two groups. The null hypothesis says the two proportions are equal, while the alternative may be two-sided, greater than, or less than. The assumptions are similar to before. The two samples must be independent, observations within each sample must be independent, and each group should satisfy the success-failure condition. For each group, we want at least 15 expected successes and 15 expected failures. This allows us to use a normal approximation for the difference between the sample proportions. Under the null hypothesis, both groups are assumed to share a common population proportion. We estimate that common value with the pooled proportion, which is the total number of successes divided by the total sample size across both groups. The test statistic is Z equals P hat sub 1 minus P hat sub 2 divided by the square root of the pooled proportion times 1 minus the pooled proportion times the quantity 1 over n sub 1 plus 1 over n sub 2. For a confidence interval, we switch to an unpooled standard error. That is because the interval is trying to estimate the true difference between the population proportions rather than test the assumption that they are equal. So in example 1, therapy A has 105 recoveries out of 150 patients, and therapy B has 72 recoveries out of 130 patients. We test whether therapy A has the higher recovery rate. The sample proportions are 0.70 and about 0.554. The pooled proportion is 0.632. The test statistic is about 2.68, with a one-sided p-value of 0.0037. We reject H sub 0 and conclude that therapy A has a higher recovery rate. The 95% confidence interval for P sub A minus P sub B is from 0.031 to 0.238. So therapy A may improve the recovery rate by about 3.1% to 23.8%. In example 2, the allele frequency is compared between male and female mice. The sample proportions are 0.30 for males and 0.133 for females. The test statistic is about 3.24, and the two-sided p-value is about 0.0012. That provides strong evidence that the allele frequencies differ between the two groups. In example 3, an online retailer compares an old layout to a new layout in an A/B test. This is analyzed using jump output. This image shows the jump test output for the two sample proportion comparison. The two-sided p-value is about 0.0339, so at the 5% level we reject H sub 0 and conclude the purchase rates differ between the two layouts. This image shows the confidence interval for the difference. The interval for old minus new runs from negative 0.0384 to negative 0.00016, which suggests the new layout performs better. The main takeaways are that this test compares two proportions. The hypothesis test uses a pooled proportion, and the confidence interval uses an unpooled standard error. We always want to interpret the result in the context of the two groups being compared.